Thanks for coming. My name is Corey Brown. I am Blue Ridge Amateur Radio, and today we're going to talk about antenna tuners. And we're going to take a different tact on talking about antenna tuners, so I hope you got your math foo on. Anyway, here we go. And I'm going to try to bounce back and forth between this seat and that because I can't see worth a damn. All right, the truth about antenna tuners. This presentation is meant to provide a mathematical proof of what antenna tuners do and how they actually work. The presentation will dispel a lot of the myths that are still hanging around out there on the information superhighway. So I'm not going to do the math, I'm going to show you the math, because the math can get really complicated, and if I were to do the math, we'd be here all night long. But you'll get to see what the math actually looks like. Okay, here's our outline. We're going to talk about tuner impedance matching. Get my pointer. Impedance matching, reflected energy, tuner efficiency, myths and legends, and then some acknowledgements. So the three things that an antenna tuner has to do to function properly is resolve reactance, transform resistance. So we're going to talk about that here. And then we're going to examine all of the power going into an antenna tuner, both from the transmitter and from the antenna, and we're going to mathematically prove where all that power is going. Okay? And then I'm going to talk about how to turn your antenna tuner into a space heater. Okay? So stand by for that. That's a real crowd pleaser. All right. Tuner impedance matching. So what do we need to know about antenna tuners? Well, first we have to understand that the environment in which an antenna tuner operates in, and that environment is an environment of impedances, right? An impedance is a combination of resistance and an imaginary number value referred to as reactance that allows us to represent both ohmic resistance and inductive or capacitive reactance that can be expressed in terms of, both of which can be expressed in terms of ohms, right? So if we were to look at resistance and reactance in the impedance plane, this is what that plane would look like. This would be dead short in terms of ohms, all the way out to wide open, right? And then above on the y-axis we would have inductance, and below we would have capacitance. And so our imaginary numbers are some amount of resistance, 50 ohms, plus some amount of inductive reactance, or minus some amount of capacitive reactance, okay? We also have, mathematically, adding impedances together in parallel leads to messy mathematics. So, our old pal, James Clerk Maxwell, invented the concept of admittance, right? So admittance, like impedance, and its subcomponents, conductance and susceptance, right? They are essentially the reciprocals of impedance. And I know you're asking, why do I need to know this? Just stand by and I'll get to it, okay? So an example of adding resistances in parallel, we have to do this 1 over business, right? 1 over this, plus 1 over that, plus 1 over the other thing. And in the world of admittance, we would simply add them together as conductance, or the reciprocal of resistance. Same for capacitors, and we would simply add them up, and we would have, in this case, because these are reactive, you would simply add the susceptance up. Again, so why is this important? Because impedance and admittance are the fundamental underpinnings of the Smith chart. Okay, everybody familiar with the Smith chart? Yes, lots of heads going up and down. Okay. So the Smith chart, believe it or not, oops, is nothing but this impedance plane that's been wrapped up into a circle. So you can imagine, this is my constant line or line of resistance. So any line going up and down across this line like this, those would be constant resistances along that line. Lines that are running this direction are lines of constant reactance. If you take this whole thing and kind of fold it up into a circle, you get this. Okay? So the Smith chart comes in two varieties: an impedance Smith chart and an admittance Smith chart. So this is a classic impedance Smith chart. And you can tell one from the other because impedances, they start on the right, 50 ohms in the middle, again, dead short on this side, wide open on this side. These circles right here are circles of constant resistance. And these arcs, like this, are circles, believe it or not, of constant reactance. So why are we spending so much time looking at this? Hold on one second, I'm going to show you. Here's an example. A lot of people use the Smith chart to figure out what the impedance will be at a particular point along a transmission line. All right, let's say you've got 100 feet of transmission line, and this circle is the, oh, let me get my head on straight, reflection coefficient. This is the reflection coefficient, that is your transmission line attached to your antenna. If the characteristic impedance of those two don't match, you get a reflection from the antenna. And that reflection is defined by the reflection coefficient. So I can put my reflection coefficient on the Smith chart, and then I can take from this point to any point on the Smith chart, which is a length in wavelengths, either from the antenna or from the generator, right? So this would be a length in wavelengths from the impedance or from the antenna. And I can take this point, draw a straight line out here to that point, say 10 degrees or 63 degrees of my feed line, and I can come up with, the Smith chart will tell me exactly what the impedance is going to be at that point. And that's that, just blown up. So here, my impedance is 0.80 ohms plus J 1.40 reactance. These are normalized values, by the way. You have to denormalize them to get to actual values. But just draw my arrow up here, and then on my line or my circle of constant resistance, I'm at 0.8, and on my constant reactance, I'm at 1.4. Okay? Why is that important? Here's the admittance Smith chart. Notice how everything starts on the left-hand side instead of the right-hand side, right? Because the admittance is the reciprocal of the impedance. Okay? Groovy. Now we're all cut up on our Smith chart. So let's go here. This should look familiar if you were here for the last show, right? SIMNEC. This is a Smith chart, but it is both a combination of an admittance Smith chart and an impedance Smith chart. And what I can do with the Smith chart is I can visualize what's happening with the components that I'm putting into my antenna tuner. In fact, I can model the load, the antenna, I can model the feed line, and then I can model the components that are going into my antenna tuner. So what's important about this? Components or reactances that are in your antenna tuner that are in series with your system change the impedance in a clockwise motion around this circle. So in this example, I'm 50 ohms at the load, I'm 50 ohms at the generator at 10 megahertz, and by putting an inductor in here in series and giving it a value of 795 795.8 nanohenries, I have moved the impedance that the generator sees to here. Right? So I'm still 50 ohms because I'm on this 50 ohm circle. See that? But the reactance has changed. And there it is right there. 50 ohms, or 50.25, and the reactance is 50. There's my reactance line, 50. And so by adding a component in series, I can move clockwise around this circle. Okay? Now I change it, I put it in parallel. Now we're going to move on the admittance circle. So simply by changing from serial or series to parallel and giving myself a value, this is what happened. I'm now going counterclockwise on the admittance or the conductance circles. And look what's happened. We have a resistance of 25 ohms, and it's 24.88 ohms inductive. So we can transform the reactance, or we can eliminate the reactance, and we can transform the ohms. And by using the Smith chart, I can see exactly what's going on by adding these components to my antenna tuner. Here's another example. Capacitor in parallel. Remember, we're going capacitive because this side of the Smith chart is capacitance. This side of the Smith chart is inductance, right? So in parallel of my capacitance, I'm now going clockwise around this circle of constant conductance. And here we are in series. And now I'm back on the impedance side, and I'm going counterclockwise around the Smith chart this way. All right, is everybody asleep yet? Okay, here we go. Now we're getting to something a little more exciting. So now I'm building an antenna tuner. So I still have a 50 ohm load. I have a capacitor in shunt, or in parallel, and I have an inductor in series, and my SWR is terrible because here at 50 ohms, I've added my capacitor and I took it all the way down here. So now what my inductor sees is 25 ohms and 24.99 negative ohms capacitance. And then by adding my inductor, I swing everything back up here and I still end up with a terrible SWR because I'm at 25.25 and 25.01 inductive. What if this was something other than 50 ohms? Like this. Oh, actually, before we get there, how would I fix this? How would I resolve that? What do I have to do? What do I have to add to this lumped circuit to get the impedance back to 50 ohms? I'd have to add a capacitor. Who said that? You've been through that. Anyway, you would add a capacitor in parallel, and you would be able to bring this right back down to 50 ohms. And there it is. So now my transmitter is happy. My SWR is 1.01 because it's looking at a 50 ohm load. So now what? Here. What if my antenna is not 50 ohms? What if it's 100 ohms and negative 20 ohms capacitive, which puts us out here? And I want to build a tuner that's going to allow me to resolve or eliminate that reactance and transform the impedance. Here we go. I'll put a capacitor in parallel. It will follow the constant line of conductance around to this point, where I will then put a inductor on, and it will follow the constant line of impedance or resistance back to 50 ohms. So this is how you design an antenna tuner. And this is what it looks like. Right? These are, when I started using this tool a couple of years ago, it was some real aha moments for me, in particular, to see what the heck is going on in here. So now you know what you're doing with an antenna tuner to eliminate reactance and transform resistance. Okay? But things are not all that rosy. Here's a chart on the impedance plane, again 50 ohms, dead short, wide open, that shows us what type of topologies, tuner topologies, we might need to use for different areas of the impedance plane. So if I'm greater than 50 ohms, if my impedance is greater than 50 ohms and inductive, I'll want to use a capacitor in series with an inductor in parallel to be able to resolve that. If I'm capacitive, above 50 ohms, I'll put an inductor on there in series and a capacitor in parallel to be able to resolve that. And things in no man's land over here, less than 50 ohms, you actually have 4 models that work best. Highly inductive, kind of capacitive, highly capacitive. And at highly inductive, you don't even have an inductor in there anymore, you have capacitors. Highly capacitors, you don't have capacitors anymore, you have inductors to be able to resolve that. Okay, so which tuner topology is right for you? It all depends on the rest of your antenna system, doesn't it? Right? So we can add another inductor on here or another capacitor on here, get a T network going, and be able to resolve this and this. And then we could do this and that and pretty much cover everything right about there. But when things get really wacky, that's when things start going. That's when you turn your tuner into a space heater, which is what we're going to see. All right, so to see how we can use various components in parallel and in series in order to eliminate reactance and transform resistance such that we can present a 50 ohm load back to our receiver or transceiver. All the above was done with SimNet, by the way. This is a free program. You can download it. It was written by Ward Harriman, and I highly suggest go ahead and download it and get familiar with it if you're into this type of thing. And before we leave this section, what happens if I put some feed line in there? So I'm just going to throw some feed line in. So there my impedance is 100 minus 20 J20 ohms, and I've put 90 degrees worth of feed line on here, or 20.83 feet at 10 megahertz. And this is the transformation. So the feed line has transformed my impedance up to a point where I am now 24.77 ohms and slightly inductive reactance, 4.69 ohms. With the feed line only, I'm at 90 degrees. I'm a quarter wave. What do I need to do to the feed line to get it back to that point? Anybody care to guess? What do I have to do to the feed line to get it back here? I have to make it 180 degrees long, a half wavelength, right? At a half wavelength, the feed line becomes transparent, and you're right back to where you were. So all the way around with the feed line, as an example. Okay, tuners and reflected energy. So here's where things are really going to get intense. Resolving an impedance generally means that you've got an impedance mismatch somewhere in your system. That's why you're using an antenna tuner, right? This generally happens at the antenna and feed line interface. But it can also happen at any other impedance discontinuity in your antenna system. An impedance mismatch between the feed line and the antenna will result in reflected energy coming back toward the source, that is, towards the transmitter. We must now explain how the antenna tuner handles this reflected energy such that it doesn't show up as SWR at your transmitter. And we're going to use math. All right, but first, a little refresher. Transmission line characteristic impedance. Everybody knows what transmission line characteristic impedance is, right? Because this is important for the formulas we're going to use. A transmission line has a characteristic impedance. We're all familiar with 50 ohms and 450 ohm ladder line. Characteristic impedance of the feed line is defined as the line's input resistance when the line is infinitely long. Specifically, it's the ratio of the amplitudes of the voltage and the current along the length of the line. And recall that the amplitude of the voltage and the current waves along the transmission line will remain the same unless acted upon by a reflection coming from the far end. So that's the whole point about the infinite line, right? If you measure an infinite line, it's going to measure whatever the characteristic impedance is, because with an infinite line, you have nothing at the end. So you have no reflections coming back. Maximum power transfer, no reflections, happens when a feed line is terminated in its characteristic impedance. This means that power applied to the line is completely absorbed by the load attached to the far end of the line if the load is the exact same impedance of the line itself. So basically, this is how you can tell what the characteristic impedance of the feed line is. You got a big roll of coax, all the lettering is gone. What's the characteristic impedance? Put a variable resistor on the far end and an antenna analyzer on the other end and tune the variable resistance until the SWR drops to 0. And whatever that reads, that's the characteristic impedance of the feed line. Question?
Yes, characteristic impedance, purely resistive or is it?
Purely resistive. Okay, why is this important to know? The formulas that we're about to look at for transmission line reflection coefficients at a discontinuity all depend on the characteristic impedance of the transmission line and the impedance directly on the opposite side of the discontinuity. I'm glad this is working. Transmission coefficient is right here. So here I have power coming from my transmitter at a discontinuity. Some of it gets through, some of it is reflected. This happens to be a current wave because the current changes phase 180 degrees on reflection, right? The formula for the transmission coefficient is 2 times where we're going divided by where we're going plus where we're coming from. So this is important. Transmission coefficient. What happened to my reflection coefficient? Here's an example of transmission coefficient. Let's say we have 50 ohms here and 100 ohms here. Based on my formula, the transmission coefficient is going to be 1.33. And I guarantee you the reflection coefficient is 0.333. I guess I must have missed the reflection coefficient. Hold on. No, it's around here somewhere.
Here it is.
Oh, there it is. Here's the reflection coefficient, right? This part here is simply where we're going minus where we came from over where we're going plus where we came from. And in this case, the reflection coefficient, 50 or 100 minus 50 divided by 100 plus 50 is 0.333. Note that the transmission coefficient is equal to 1 plus the reflection coefficient, because this is an example of the maintenance. What's the word I'm looking for? We're losing no energy in this reflection, okay? And here we are again. Here's our transmission coefficient formula. Here's our reflection coefficient formula. This is 50 ohms. This is 100 ohms. So that's what's happening at that boundary. Conservation of energy, that's what I was looking for. We have conservation of energy. Okay. The question is, why do the transmission coefficient and the reflection coefficient only take into account the impedances directly on the other side of the border at the discontinuity? Why don't the formulas consider the total impedance of the rest of the system instead of just the differences at the boundaries? And the answer is, think of the power coming from the transmitter as a single impulse of power, a photon of light, right, coming out of the transmitter. This impulse of power can't see into the future. It has no idea what's on the other end of the transmission line. Could be a short, could be an open, could be an infinitely long line, could be an antenna, but it can't know. It doesn't know what the future is until energy has made it to the end and come back. Only at that point can you determine what the actual impedance is of the system. Over time, as we're pumping energy into the system, over time there will be reflected signals, and a steady state of forward and reflected power will stabilize in our system. And it's at that point that we realize the impedance of the entire system. Okay. Quarter wave transformer. Everybody knows what a quarter wave transformer is, right? Shake your heads. Yes, yes, okay. For those of you who don't, this is my generator, this is my transmitter, this is my 50 ohm coax leading out to my antenna. It's 50 ohms, my antenna is 200 ohms, and I want to put something in here. I want to put a quarter wave transformer in here that will resolve the reactance, or in this case there's no reactance, but resolve the resistance, right? And so the formulas for quarter wave transformers are the square root of the squares of these means, right? 50 squared, 50 squared, square root of those added together gives us 100. So our quarter wave transformer needs to be of 100 ohms, and it needs to be 1/4 wavelength long at the frequency of operation, right? To resolve 200 ohms down to 50 ohms. So in this, we now have reflection coefficients. See that? Reflection coefficients and transmission coefficients. So this is how we're going to be able to find all the power that's going into the system and where it's going. Oh yeah, it looks that bad. Here's the first impulse of power coming from the transmitter. It hits the boundary at the quarter wave transformer, and it reflects, and it's done. Hits that reflection point, and it's done. Stops right there. But there's a transmission coefficient here. So this is one impulse of power. This is not steady state. This is one impulse of power. Hits the boundary. There's a transmission coefficient here. So some of that power goes through, hits the antenna, where some of it goes through and some of it reflects. And again, at this point, there's a reflection coefficient and a transmission coefficient. So some continues through, some reflects back, and so on and so forth. It goes until we reach steady state. Okay, so this is what we're dealing with, and that's what the math looks like. And that's just for one reflection. This is represents the math as an infinite series of reflections and re-reflections, and you have to add them all up to know what the power is in any one particular direction. But looks awful. Fear not. Through a couple of cycles, the reflections have become smaller and smaller over time, and the steady state formula allows us to do this a lot easier. Okay, so here we are. We can actually write this as steady state, and I'm going to show you why in just a second, because these numbers fall off very rapidly, right? So this is just for one reflection, and given this formula, I can come up with an apparent reflection coefficient. Keep that word in mind, apparent, because it's important. Note that in a matched system, the apparent reflection coefficient right there goes to 0. That reflection goes to 0, apparently, in a matched system. So let's go back here. Now we can start putting some numbers to this. So I've got 1 volt coming from my transmitter. It hits my reflection coefficient, which is what? 0.333. 1 times 0.333 is 0.333 volts. Goes through 1.333 volts, and back and forth we go. But look what's happening to the numbers. 0.333, negative 0.296. negative 0.033, negative 004, negative 00004. So you can see in very short order, the power falls off drastically, right? And that's why we can come up with a shortcut for that infinite series to come up with the values for reflection and transmission. Same thing's happening over here. 1.333, 148, 016, 002, and finally on the outbound side. Okay? Yep?
When that first reflection happens and it goes back to the transmitter,
Yep.
what happens when it hits the
Transmitter is 50 ohms, so it's absorbed in the transmitter. But it's happening in the blink of an eye, right? Because all this, at 10 megahertz,
would that tend to heat up the transmitter?
no, what it will do, it will
It's so small.
the impedance will shift slightly, right? And that will affect the output impedance of your PA, and so your power will be adjusted down until things go back to a steady state. Okay, so again, we have to add all these up to figure out how much power is coming back, add all these up to figure out how much power is going that way, and then add all these up to figure out what power is actually going to the antenna. So two things on this that you're probably scratching your head on. Why is that number negative? And how can that possibly be bigger than the power I'm providing from my transmitter? Right? How is it, if I put a watt meter right there, how is it that I'm getting more power out than I'm putting in? Right? Because this happened at essentially T0 seconds, right? This happened, and this, and this, and this, at T0 minus 1, minus 2, minus 3, minus 4. So you've got new power combined with old power and giving you what apparently looks like more power going out than you're putting in. But really, it's just time. And your transmitter's acting like a pump. Now, why is that number negative? And why is it when I add that together, I come up with 0 volts? It's because, how long is that? It's 90 degrees. 90 degrees out, 90 degrees back, 180 degrees. My voltage is now 180 degrees out of phase with the incident voltage coming from the transmitter. That's why that goes negative. And we'll talk about this negative here in just a second. Remember, this is reflection coefficient. This is not the transmission coefficient. So our numbers are negative here because of the time delay. It went 90 degrees this direction, it went 90 degrees that direction, and so that, incident voltage is now 180 degrees out of phase with the reflected voltage. And that's important. Take a look at this. This is a simulation done by Jeff Anderson. This is what happens when the transmitter is initially turned on. These are reflections coming from the input side of a quarter wave transformer. That's what we're seeing. As the ping-ponging gets going, this power falls off to 0. As soon as you turn the transmitter off, the reflected voltage comes right back and it fades off to 0. Everybody okay with that? Can you see it? Yeah? How about now? Here's our reflected voltage. Here's our initial reflection. Every single pulse of power coming is going to hit this, and there's going to be a reflection. There is a transmission coefficient here going this direction, so reflected power from the antenna is coming this direction, and lo and behold, they are the exact same value, and the voltage drops to 0. So what happens when this drops to 0? SWR goes to 0. SWR goes to 1.0 to 1, because you have no more reflected energy. But the reality is, it's there. It's just being destructed, right? These two, the voltage here are adding destructively to 0. And believe it or not, this is how all antenna tuners work. The match is at the input side of the antenna tuner, or what Maxwell calls the matching point of an antenna tuner. Okay? Questions? I'll show you. All right, so if you take one thing away from this presentation, this is it. This transformer became 50 ohms because of the cancellation of these two waves, right? Just putting it out there, connecting it to your antenna, did not make that endpoint 50 ohms. That endpoint became 50 ohms when the power from your transmitter, that reflected power from your transmitter, got canceled by the re-reflected power from your antenna. Cool? Everybody's looking at me like I'm crazy. Here's a quarter wave transformer. We can skip that. Okay. Quarter wave matching transformer. What are the takeaways from this? Quarter wave transformer works best when the system is purely resistive, not reactive. I'll show you some charts later. I'll show you what happens when you put reactance in there. The solution to the impedance mismatch that we have corrected with a quarter wave transformer works exactly the same way in more complicated antenna tuners, which is what we're going to look at next. Reflected waves are a fact of life, even in perfectly matched systems, because there's no such thing as a perfect match or a lossless transmission line or no environmental impacts, right? Reflections are there. Reflections happen at the input side of the antenna tuner as well as on the output side. This is true regardless of whether the match is through a quarter wave transformer or through a T network or L network or pi network. They all represent a second discontinuity in the transmission line. The quarter wave transformer presents a 50 ohm load to the transmission line because of the reflections being canceled. That is, the apparent reflection coefficient goes to 0. Okay, remember I said apparent? All right. Now let's look at something a little more complicated. This work that I'm about to share with you was written up by Dr. Stephen R. Best, VE9SRB, back in 2001 and was published in QEX magazine over 3 monthly periods. Right? This information is still available in the QEX archives. So if you want to go to QEX and download this work from Dr. Stephen R. Best, you can still do that and you can read it, and he does a fantastic job of telling you everything that I've just told you and I'm about to tell you. Our pal, Walter Maxwell, W2DU, had some issues with Stephen's work, and Maxwell published a rebuttal, if you will, in 2004. Just one article, again in QEX, and that paper is still available, right? So you can go to QEX and download both these papers. Because of this turmoil, Jeff Anderson, K6JCA, redid all of Best's work in 2021. And what he found was that Best's work was completely accurate, and it was obvious. You can go read Anderson's work as well. There's a link to it. He found that Maxwell had misinterpreted early on what Best had been doing. And so, but it's interesting though, that both Best and Maxwell basically came to the exact same conclusion, but Walter Maxwell didn't like the way Best did it. So Jeff Anderson redid all this work recently, and you can go read it, and that's where a lot of this comes from. So now we're going to use an LC network. So I don't have a quarter wave transformer anymore. I just have some 50 ohm transmission line length doesn't matter. 50 ohm load, 50 ohm transmitter, 150 ohm load, so there's going to be some reflections in here. And I've got some components set up to cancel the reflections to get a one-to-one SWR. So that's our playground. Okay? Now we need to understand how this impacts the calculations for the reflection coefficient and the transmission coefficient, because it's all still there. So we can look at this as a lumped element, two-port transmission and reflection coefficient. Because these elements are directly on the other side of the boundary to the input of the antenna tuner and the output of the antenna tuner, we can use these values, reactance values, in our coefficient formulas and come up with new reflection coefficients, transmission coefficients on both sides. And then these, same old thing, 50 ohms going into 150 ohms, going to give you some amount of transmission coefficient and some reflection coefficient. So the math just gets a lot worse, but it works exactly the same way. So now when I'm calculating my reflection coefficient, I have to take components in parallel with transmission line and in series, and while the math gets really ugly, you end up with values for reflection coefficient from the transmitter looking into the antenna tuner. And you end up with reflection coefficients for the reflected waves coming from the antenna going into the antenna from the output port. And you'll notice that these formulas are quite a bit different than the simple formulas we looked at previously. But it's the exact same thing. And here's what the infinite series looks like. 1, 2, 3, 4 sets of infinite series of power that we have to add together to get the actual power flowing through the network, or the voltage flowing through the network. And once again, we can reduce these down to a simpler form. Instead of having to use an infinite series, we can use a much more palatable mathematical equation. But it all comes out the same. The reflection at this point in our matching network is eliminated by the re-reflections of the power coming from the antenna. So here's our steady state diagram. 0 volts. Right? So as soon as we have things tuned up, that reflection from the transmitter is canceled by the re-reflection from the antenna, and we are tuned up. Now my transmitter sees 50 ohms and is happy and gives me a good SWR. Questions? Have you seen this stuff before? Who's seen this stuff before? I see him over here. Right? Everybody else? Have you done reading at this level yet? Right? This is good stuff. And you can go back and read Best's work and Maxwell's work and Anderson's work. It really is eye-opening. Antenna tuners are doing a hell of a lot more than simply resolving an impedance, right? So Best's conclusion, in order for Best's conclusion to be correct, the reflected voltages at the input of the tuner need to be equal in amplitude and opposite in phase. And they are. Although I left out the calculations for the phase, if you take the phase of the first reflected voltage and the phase of the re-reflected voltage, add them together, you get 180 degrees. So 35.35 volts, 35.35 volts, 180 degrees out of phase, and they're gone. The same thing's happening on the current side, by the way. The exact same thing is happening on the current side. This is voltage, but in terms of current, the exact same thing is happening, and they are canceling out. Okay, so I skipped over a lot of the mathematics, especially for the angles, but these are the resources that you're interested in, and we'll get to the power thing in just a sec. Jeff Anderson, this is he's got some really, really good information out there. It'll take you months to go through this stuff. And then these are the articles in QEX that you can download. As long as you're an ARR member, you can go to the QEX archive and download these articles and read it. By the way, Walt Maxwell's rebuttal was not very friendly. He had some harsh words to say about BEST. But that's okay. We've all learned from it. Here's Walt's rebuttal, by the way, again, in QEX, where you can go to get it. Oh, so while Maxwell may have disagreed with some of what BEST wrote, it is clear that in the end result consisting of wave cancellations at the input of the tuner is the same. Walt, of course, concentrated on conjugate matching, while BEST concentrated on amplitude and phase. And that work was verified by Jeff Anderson in 2021. Okay, here's the part you've all been waiting for. How to turn your antenna tuner into a space heater. All right? For the most part, antenna tuners are highly efficient parts of your antenna system. Keep in mind that there's not much difference between an antenna tuner and a PA tank circuit in your favorite boat anchor. Antenna tuner components are mostly reactive in nature and not resistive. But there are limits, of course. Inductors, in particular, in an antenna tuner are the major culprits when it comes to losses, when tuning vast excursions into the impedance plane. An inductor becomes resistive when the amount of reactance dialed into the roller inductor goes up and the Q of the component goes down, right? So roller inductors don't have a steady Q. They have a high Q when there's very little inductance, but they have a pretty low Q when you dial up a whole pile of inductance. And so our resistance at any time is equal to how much inductance we've got dialed in and the Q at that point. So when the reactance of the inductor and the Q quality go down, or as the inductance goes up and the Q goes down, the resistance in an inductor becomes more of an issue. Where it really becomes an issue is with an antenna system that presents a very low resistive values with very high impedance or reactive values. And here we go. So here's my antenna, and this is actually modeled a 40-meter dipole using SIMNEC, and I'm driving it at 80 meters. And this is what's happening. The resistance or the impedance seen by the inductor is 13.29 ohms with a reactance of 1178 capacitive. And because of that, this inductor is burning 310 watts of power for 1,000 watts going in. So 1,000 watts going in, 310 going up in smoke, 687 going out to your antenna. Is that a question? I'm sorry, I'm having a hard time hearing. Here, this is worst case scenario. Let's make this into a pi network. Same values for my antenna, because that's a 40-meter antenna, still driving it at 3.8 megahertz. Now I put a capacitor in shunt, and look at the resistance that my inductor is now looking into. Less than half an ohm, 0.4744 ohms with a reactance of negative 201 capacitive. And lo and behold, we're burning 681 watts. We're losing 681 watts in our inductor with 1,000 watts in. So that'll definitely heat up your shack. Right? So now we'll make things better. And we'll use the exact same antenna at 40 megahertz like it was supposed to be used at. And now our power consumption in the capacitor is 0.26 watts. And the power consumption in the inductor is now 5 watts with 1,000 watts of power going in. So what's the what's the story on this, right? Your antenna tuner is 1/3 of your entire antenna system, right? If you measure the impedance on your transmission line and your antenna, and if you're getting some real excursions in the impedance plane that is very low resistance, very high reactance, chances are you can tune it, but things are going to get hot. Okay, myths and legends. I only have one slide. Antenna tuners just fool your radio into believing there's a match. Who believes that now, after seeing all this? Does it fool your radio? No. Antenna tuners burn up reflected power and send it to ground. That's a beaut. I was actually told that on an internet forum. Burn? I've been looking for that combination of components and antenna tuners for years, and I still haven't found it. The one that burns up reflected power and sends it to ground. I love that. I don't need an antenna tuner. My antennas are all resonant. Cool. Resonant antennas radiate better than non-resonant antennas. While not a tuner myth specifically, it goes with this last myth. A tuner will improve antenna performance. False. A crappy antenna is still a crappy antenna. And my Johnson Viking kilowatt matchbox will tune the bed springs on 160 meters. How many of you have heard that over the years? Gutters, bed springs, all that. It sure will, but it also makes a great space heater. Acknowledgements. Huge shout out to Jeff Anderson, and I actually spoke to Jeff quite a bit when I was making this presentation. He was the one who enlightened me with his work back in 2021. Great guy. Rick Westerman in Germany, DJ Zero IP, he helped to review this work. Huge shout out to my friends at Watauga Amateur Radio Club in Boone, North Carolina for their help and encouragement. And to Ward Harriman for his use of SimNet to do all these nifty diagrams. And so you can get to Jeff's work here, Walt Maxwell's work here, Steve Best here, and a lot of this also came from David Knight. He's an SK now, just like Walter himself. But David Knight has a really good site, and he's got a really nice book on AC theory on his site. So if you really want to understand this stuff, you've got to know about AC theory, and that's where to get it. So here's Rick's site. He's a good aggregator of ham radio related stuff, so that's a good place to go. And then Ward Harriman, this is where you'll go to download a copy of SimNet. There's Jeff Anderson, Stephen Best, Walt Maxwell, of course, David Knight, and me, Doc Brown. Thank you.